So for this problem, here's what they were looking for. And so you know how we were looking at the boards and I was talking about what some boards had and what some boards didn't have. So this board had that beautiful left and right-handed limit to support for the final limit. This professor counted that for a point. You had to have the left and righties to get that point, right? And the whole exam, you're talking a 4-hour exam, is only 108 points. A point is a big deal. So you want to make sure that you're writing enough to justify. Now, when you look at scoring guidelines, on the left, they're going to show you all the work that they did for the problem. And on the right, they're going to show you the points assigned, right? So for this one, this is the work. You don't have to show everything here for those lefties and righties. You just need to make sure that you show them, right? If you have that, that's okay. That's acceptable. All right. And then, of course, therefore the limit. So now the final thing is the answer with explanation. So you've got your limit, your function, they equal each other, therefore it's continuous. So this professor did it in a 3-stepper. Some professors just do the nice little 3-way equation that I put the star over there on the board by. So you can, either way is fine, right? Everybody, like, that's a generally accepted thing that you can either write it in 3 steps or you can write it in the big combo step, and that's fine. They don't care. So anyway, so 2 points. This part of this problem was worth 2 points. Just so you know, this was a part C. Question 4. How many questions are in free response? 6, right? So very good. So this was question 4. Question 4, because it's number 4, it tells me it's a no calculator question. Questions 3, 4, 5, and 6 are no calculator. Almost every single question, I think I'm going to say every single question has multiple parts. Most of the questions, the free response, have 3 or 4 parts. So this one was part 3 of what I think was a 4-part question. So anyway, from 2012. Any questions on this little continuity question? All right. Something very similar to this might show up on your test, right? Your test is certainly going to have some multiple choice and some free response on a lot of different topics. Today, we are diving into our first, real theorem, right? I mean, ignoring the squeeze theorem. This is our first real meaty theorem, a theorem that we have to know, understand, be able to state, be able to apply, be able to justify. We're going to break this theorem down, and we're going to make sure that we understand not just this theorem, but the whole concept of theorem in general. So in math, you might not know this. Do you all understand the difference between a theory and a theorem? There's no such thing as a theory in math, right? When I hear the word theory, like, oh, I have a theory, that's kind of like an idea, right? It might be this, right? A theory is not the same thing as a theorem. Don't confuse them. A theorem is something that is absolute fact. It has been proven to be true, always, forever, no exceptions. So in math, we use theorems in order to advance our math forward. If you come up with an idea, like, I really think that this is going to work, mathematicians won't even look at it until you've proven that it works. So if you come up with an idea, the idea is great, but until you can prove it, you will never be allowed to actually put it into any type of a publication. So all of mathematics is based on ironclad fact. There's no gray area. There's no sometimes. It is 100%. Everything is true. It is all fact, and it's all been proven. So I kind of like that about math. Like, you can't argue because it is. Like, there's no argument. It's proven. This is it, right? So that's kind of like, I'm a very linear kind of a person. I like that about math. I like, if this is true, done, right? Not, if this is true, then, well, maybe. I don't like the well, maybes. I like, yeah. So anyway, So today we're going to do our first theorem, and we're going to really break it apart. We won't spend this much time on most theorems, but I really want you to understand the concept of theorem. While you're writing, you can go ahead and take a minute and write it down. I'm going to talk to you about high-level math. I am hoping that at least a couple of you in this class, if not now, maybe later on in the year, feel inspired to at least seek out higher level math. I know that like a lot of you will probably take higher level math if you plan on going into like engineering or some sort of a mathematical field, actuarial science, right? Those are all like mathematical fields where you have to take high level math. But every once in a while, I have a student who just loves pure theoretical math. They don't need to apply it. They don't need to use it. They just love the math for the math. And there's nothing wrong with loving math for math itself. I love math. It's kind of like some people love art. Some people love music. My comfort is in math. I love math. And because of that, I love like pushing myself into harder and harder math. Like that to me, it's hard, right? My brain hurts, but I like that. That's a good place for me. That's enjoyment for me. If you enjoy that, right? Be a theoretical mathematician, right? Become a math professor and just spend your time trying to propel math forward. We've come an enormous amount of distance since the 1700s. The 1700s was a big explosion in math, right? Math progressed like crazy in the 1700s and the early 1800s. That was when we went from just like simple algebra geometry, all of a sudden you got calculus, bam, and like the whole world opened up. So, and then it just got higher and higher. Now, when I read what mathematicians do their theses on, like most of it, I don't even understand just the topic, much less like what the gist inside of it. It'll just sound like Greek to you when we get onto our further Mathematician Mondays with more current mathematicians. But don't be intimidated. Don't be scared. You can do this, right? Every mathematician is just a human being that was sitting in a classroom years ago, right? Just like you. So there is glory, there is beauty in theoretical math. So don't shy away from it or dismiss it as though it is a taboo field. It's a good field. You might not like become wealthy. You never know. Maybe you'll publish a theorem, right? So who knows? Maybe someday I'll open up my textbook and I'll be reading the Tran theorem, right? Is it Tran or Tron? Tran? Do you know that my maiden name is Trantham? Same first four letters, T-R-A-N. Yeah. So anyway, yeah, we'll read the Tran theorem, right? Tweet Ian, she's going to propel some sort of field of mathematics forward. Are you? You never know, right? The world is endless. Possibilities. You never know. Never pigeonhole yourself into saying, I wouldn't do that. You can do that. Like, that's the one thing that I regret from when I was younger, was assuming that I couldn't do things. Never assume you can't do anything. You can do something. You might have to work hard, but you can do it, right? I don't know how to play the saxophone, but I'm not going to say I never could play the saxophone. It might take a lot longer for me to learn it than some other people who are really intuitive with it, but I could do it if I worked hard enough, right? You can do it. It just might take some work, but you can do it. All right. Anyway, wow, that's a lot of pep talk for, okay. So intermediate value theorem. Every theorem in math has what's called a hypothesis and a conclusion. The hypothesis is not the idea. Again, it's not like a theory, right? The hypothesis in math is like, theorems are like if-then statements, right? How many of you guys have taken computer science or had any? Okay. If you've had any experience in computer science, you know if-then statements, right? So I was just as an undergrad, I was a computational math major, so my major was half computer science and half math. But the computer science that I was doing was like Pascal, right? It's like there was no internet back then. It was real different. But programming, like if I look at programming today, like I don't know Java at all. Like I wouldn't know it if it walked up and shook my hand. But I can still like look at a basic program and kind of understand what's going on, right? Because most programming languages are if-then statements. If this is true, then you do this, right? If this is true, then you do that. Theorems are if-then statements. If this is true, then this is true. If this is true, then this is true. The if part is called the hypothesis. The hypothesis basically contains the conditions that have to be met for the theorem to apply. If these are true, then this is going to happen, right? So you have to meet the if these are true first. They're like the conditions that have to be met before you get the conclusion, which is the then part, right? Hypothesis, conclusion. So in this problem, or in this theorem, we need to state the hypothesis. The hypothesis, it's not scary. It's just all the words that come after the if until you hit the then, right? So let's do some calling. Gavin. Hi, Gavin. What is the hypothesis of this theorem? Can you read the hypothesis? Okay, that is what a hypothesis is. For this particular theorem, the hypothesis is everything that comes after the word if before you hit the word then. Tell me the hypothesis for this theorem.
If f is continuous on a, b, and n is a number between fa and fb.
Good. That's it. That's your hypothesis. Now, when we say fa, do we say fa or do we say f of a? F of a. Get in the habit of saying f of a. The first period also just said fa. So we got to get in the habit of reading function notation out loud. F of a. A is an input for that function f. Okay, so our hypothesis is this. F is continuous on the closed interval from a to b. I call it closed because it's enclosed in brackets. When you're enclosed in those square brackets, do those mean include the endpoints or exclude the endpoints? Include the endpoints. We also can say this is an inclusive interval because it includes the endpoints. So if f is continuous on the closed interval from a to b, and n is a number between f of a and f of b. So Faith, look at this hypothesis. How many conditions have to be met for us to apply this theorem? You're really close. Anyone want to give her a little hint? It's just two. Very good. So can you tell me one of them? What's one of them? Okay, so the first condition that has to be met for every single theorem that we're going to use this year is that the function has to be continuous. So every time you are applying a theorem, the first thing you're going to write every single time is f of x is continuous on, and then most of the time it's on a closed interval. So for this one, this first part, that's like the first condition we have to check. Is f continuous on the closed interval a to b? That's like condition number one. Okay, so now let's say yes, f is continuous. We're not ready to apply. We've got one more thing to check. So Faith, what's the one other thing that we have to check? N is a number between f of a and f of b. If we're on a closed interval, these are like the endpoints of the interval. We're going from A to B, starting at A, ending at B. F of A and F of B, what would those be? If A and B, are those X or Y values if I say I'm going from A to B? Those are X values. What about f of a to f of b? Those are y values, right? So these are the y values of the endpoints. N is just some random number. So if n is some random number between the y values of the endpoints. So function's continuous, and you pick some number that's between the y values of the endpoint. So I start here, I end here. N is any number in between, right? If those two conditions are met, if those two things are true, then we get the conclusion of the theorem. So, hi Kirthana. All right, can you read to me the conclusion of the theorem? That was perfect. Beautiful. Beautifully read. There exists a number c in AB. Is c an x value or a y value? Are you sure?
Yeah.
Yes.
How do you know?
It's not
F of C.
Very good. Okay, there's two tip-offs. One, C is in the interval from A to B, and those are X's, right? So C is in here, it's an X, such that F of C, C is an input, equals N. So, very well done. So that's the conclusion. This is the conclusion of the theorem. There exists a number C in AB such that F of C equals N. That is all great. And you can write out, I'm hoping now, after doing this, which we're spending a lot of time on, but that's okay, you can look at a theorem and break apart the hypothesis and the conclusion. The next step is knowing what it means, right? That's kind of the hard part, and that takes practice. Being able to read a theorem and understand what is it saying, right? That really just takes practice. There's no easy way to teach you how to read a theorem and interpret what it's saying in like regular non-mathy talk, right? Yes, Jennifer.
So for the first part of the hypothesis, why is it bracketed in A and B and the second part is
That is a part of the theorem that we'll talk about that. That's part of the result. Yes.
When it says n is a number between f of a and f of b, is that inclusive or
That's a good
exclusive?
question. So, n can be at an endpoint, but then your c would also have to be allowed to be at an endpoint. So because c has to be in the open interval, we would say then that n has to be it would be non-inclusive. That n has to be literally in between, not equal to. Yeah. And I will tell you in all honesty, some books put this closed and put this closed. Some books keep this open and then keep this open. So it just varies from book to book how they've chosen to present it. The gist of the theorem is the same either way. But yeah, this particular book keeps this open and keeps this open. I like the open better. I'm pretty sure your last book, it was all closed. I like the open better because the next two theorems we're going to learn have a very similar setup, and also not just in the book, but like the whole world is open. So it's good to kind of get in that habit now that the answer has to be in the open interval. All right, what does this mean? Does anyone know what it means? Can anyone explain it in? Wait. Let's see, Ishan. All right, I'm ready.
So it's like if you have a graph,
Uh-huh.
and then any number on the graph will have an x value for it.
I love it. That's actually a pretty good explanation. So have you done this before?
I just read it.
Well done. All right. Okay, so so Ishan was saying, hey, look, if you've got a graph, so that's what I've got on the next screen are some graphs, right? It's easy as, I'm very visual. So for me, if I see it, then I'll understand it better than if you just talk to me about it. So, all right, here's what it says. Say you've got a graph. Say this is your f of x, right? Here's A, here's B. So beginning, end. Here's your f of A, right? I'm going to write big so you can see. F of A. Here's your f of B. So these are the y values of the end points, right? It doesn't matter if it's going up or going down, but you've got a beginning and an ending on the x-axis, and you've got like the end points on the y-axis. The graph, just so you know, it can continue. It's not like this only applies to segmented parts of graphs. The graph can be continuous on the whole real number line, but the theorem is only focusing on a part. So this theorem is always talking about a closed interval. So even if the function continues in both directions, we're only looking at some part of it, some beginning to end, a to b. All right, so what does the theorem say? The theorem says if we pick any number between these two numbers, so call it n, if we pick any number n between the two y values of the endpoints, there has to be some x on the function that has that as its y value in between a and b. Now, that's repeating the theorem. Let's talk about what it means in, like, on the street. Like if someone came up to you on the street and said, can you please explain what the intermediate value theorem says, right? So what would you say? Here's what you'd really say. You would say, to get from A to B, I have to hit on a continuous function. To get from A to B on a continuous function, I have to hit every y value in between them at least once. That's what it's really saying. It's really saying if you got a continuous function, and you're going from A to B, you got to hit every y value in between those at least once. Can you hit them more than once? Sure. Here's one right here. Like here, if we just move the n down a little bit, like now we've got our n over here. Whoa, we've got here and here. And we've got all of these different spots, right, with the same y value. That's okay. You just have to hit it at least once. There is no way on a continuous function to go from here to here without hitting every y value in between. Think about it for a moment. Search your heart. You know it to be true. There is no way to go from here to here on a continuous function without hitting every y value in between. Right? Even if you went like way down, right, and then came back, you're still hitting all the y values. You're just like hitting them in a little space, but you're still hitting them all, right? There's no way that you can do it without hitting them all in between. That make sense? Okay. All right, so that's the gist of the theorem. Now, how do we apply it? Books often apply the theorem by making you find a zero. The College Board usually doesn't use this theorem to find zeros, but books do, so because of that, we're going to do it. So even your old book does, your new book does, every book I've ever seen always starts with, hey, use it to prove there's a zero. So first question I have for you, so if you want to, like while I'm talking, if you want to write down this is our first example, show that there must be a zero on the interval from 0 to 1 for f of x equals x cubed plus 2x minus 1. I'll give you a moment to write, and then I'm going to ask you more questions. So first thing my first question to you is, if we have to show there must be a zero, is a zero an x value or a y value? It's a y value. To show that like x is 0, that's just like right there, like, hey, x is 0, right? So we're not saying like, where is x 0? Because we know where x is 0, it's 0 at 0, right? We want to know where y is 0. So you're finding all the x values where the function crosses the x-axis, right? Those are called the zeros of the function. They're also called the roots, right? You also ever call them roots, right? Or solutions. Okay. So anyway, I never liked solutions because, like, how does y solutions always mean like the zeros? I never liked that because to me, a solution is just a solution to some problem. It doesn't have to be where are the zeros. But anyway, so we're going to find a 0 on this interval for f of x equals x cubed plus 2x minus 1. So we're going to show this, we're going to use the IVT. What's the first, I'm going to ask a person here. So, Anthony, how's life?
Pretty good.
Are you really? Oh, I'm sorry. I think you can answer this question. If you can't, that's okay. Your group can help you, okay? All right. For this theorem, and actually for every theorem going forward, what is the first thing you need to check? What's the first condition that has to be? See, you rock, right? Even though you're tired, you're on fire. All right. So the first thing you have to write, f of x is continuous on 0, 1. Check. And you don't have to put the check mark. I do. That's my personal thing. I always put, and I make the sound too when I'm making my check marks. So it helps me remember. Like, I know that there are 2 check marks for IVT and NVT. I know there are 3 check marks for rolls. I remember the check marks. There's 1 check mark for EVT. I remember the numbers of check marks, and it helps me make sure I put them when I'm writing out my answers. Okay. So f of x is continuous. Anyone know the second condition? You guys have it in your notes somewhere. Tyler. Good. So for this problem, what's our n? It is 0. Well done. So we need to know that 0 is between f of 0 and f of 1. How are we going to know if 0 is between f of 0 and f of 1? What would be, Tyler, what would be good things to find? What would be good things to find? We don't know if 0 is between f of 0 and f of 1 because we don't know f of 0 and f of 1. So what would be good things to find? F of 0 and f of 1, right? So take 10 seconds, find f of 0 and f of 1. I give you 10 seconds. It starts now. Time's up. What's f of 0?
-1.
-1. What's f of 1? 2. All right, very good. So is 0 in between f of 0 and f of 1?
Yeah.
Yes. Then you got to write it. F of 0 is less than 0, which is less than f of 1. That is the mathy way of saying 0 is between f of 0 and f of 1. You write it as a compound inequality. Ian, are you stuck? Do you? Okay. Did you guys never, like, I know you've seen these. When you see these, do you think this is between those two? That's what your brain should be thinking, hey, this is between these two things. Wait. Anisha.
Yeah. How do you know that it's continuous?
Good question. I didn't even talk about that. Okay. That's such a good question. So when you're checking your conditions, if you have to check continuity, you don't have to prove continuity. As a matter of fact, it's like really hard to prove continuity over an interval. Like, you can prove continuity at points, right? You all proved continuity at -3 this morning, but to prove it over an interval is really tricky. You will never be asked to prove continuity on an interval. You just have to check it, right? So how do I know that this function is continuous? How do I know visually by looking at it? Yes, Casper. It's a polynomial. All polynomials are continuous, right? Why? Because you're never dividing by 0, right? No holes, no asymptotes, no jumps. It's not piecewise. It's just a plain old polynomial. We love polynomials. Polynomials are always continuous. Yeah. You don't have to prove why. You just have to check it and write it. All right. Once in a while, we might throw one in there that's not continuous, just to see if you're paying attention. Right. Okay. All right.
Wait,
So, oh,
sorry.
yeah, no, yes, okay.
So if it isn't continuous, do you just not?
You would say IDT does not apply, so because f of x is discontinuous. Yeah. And it might be nice to say where it's discontinuous or whatever, but yeah. Ari.
How do you find it?
So in this case, it said show that there must be a 0. It's whatever number you're kind of investigating. So the next problem will be more obvious, and this one it was written in letters, so it's kind of hidden a little bit more. But whatever y value you're curious about, that's your n. And I should also mention, I'm sorry I'm talking a lot today, but I should also mention that this book uses n. Every other book I've ever seen calls it k. So in your, maybe on quizzes and stuff, maybe you might see on a quiz or an AP problem, or even maybe on your test. I don't think so, but you never know. If you see it called K, that's the same thing. It's just this author chose N. It's the author's choice on what letter they pick. So they picked N, and some people might call it K. All right. Okay. So are our two conditions met? Is the hypothesis met?
Yes.
Yes. Then you just write your answer. So how do you write a conclusion statement? Most important lesson of the day. Don't worry, you will be doing one of these on your own. We're taking 25 minutes to set you up. How do you write a conclusion statement? You rewrite the problem without any question. So if the problem says, show that there must be a 0 on the interval 0 to 1 for f of x, then your conclusion statement would be, therefore, by the insert theorem name here, there must be a 0 on 0 to 1 for f of x. You just you write therefore, by the, and state your theorem. And you can abbreviate therefore. Do you remember how to abbreviate therefore? 3 dots, right? Okay, therefore, by the IVT. Do you want more abbreviations or no? Do you want me to show you some mathematical shorthands? Okay, so there must be, that's another wording for there exists. When you write there exists is a backwards hard E. So if you write, you don't have to write, you just write the words, honestly. I should probably just be writing the words. There exists a 0 on 0 to 1 for f of x. I'm going to teach you another abbreviation in the next problem. Okay. So just so you know, this E here means there must be or there exists. There exists. This one right here means therefore or thus. My last professor over the summer never used the word therefore. He always used the word thus. And I was always trained to say therefore. But he didn't take off. I always wrote therefore. So wait, Luke.
Do you not have to say because
You've just done that right here and here. This is your hypothesis, the hypothesis has been met, therefore it's got to be true. Done. Yep. So yeah, you justified above and then wrote your conclusion. Good. Any other questions? Because you're about to do one. Finally, right? Here we go. All right. Show that there must be at least one value c in the interval from 5/2 to 4 such that f of c equals 6 if f of x is x squared plus x over x minus 1. So in your groups, or you can silently work for a couple minutes, like a minute or so. In your groups, though, I want you to make sure that you've written out and checked your hypothesis, and then you've written your conclusion statement.
For continuous, you just have to say it's continuous, right? You don't have to do it
Yeah, you don't have to prove continuity. Make sure you do check that it's continuous. I got my new stools, but
I know, they're so cute.
aren't they cute? I know, I love them too. Except they wrapped the top in this plastic and then screwed the legs on.
Oh.
So
That's kind of dumb on their part.
I know. So I'm having to pull all these pieces of plastic off.
The legs in there.
Yeah, like they wrapped the tops first. I mean, they were every single part of this stool was wrapped. Like there was no scratches. Like it was wrapped in plastic, but the top was in plastic first, and then they screwed the legs on
Through both sets of plastic.
through all the plastic. Yeah.
That's kind of
So yeah, and the plastic for the legs too was on the legs before the screws. So like there's double layers of plastic under here.
At least you can see them.
I know. So I need to bring in a screwdriver. We actually have a math department toolkit. I could go get a screwdriver. But what is up with visitors during the second period? Like, why do people keep coming in here?
Is that the new
See,
assistant
that kind of
principal?
That's the new assistant principal. That's Mr. Osmond.
That's like a
So he's the one who just did the announcement. Yeah, that's his first name's Akram. He's really nice.
I'll give you a calculator.
He said hi to me. I like it when people say hi to me.
Good. People should say hi, right? I like whenever if you ever are walking by someone in a hall, do you make sure you say hi even if you don't know them?
Well, like sometimes.
Well, yeah. I mean, these halls are 3,000.
I like smile at them.
Say you're like somewhere else and you're walking and someone else is coming. Like say you're outside for a walk, right? And someone's coming up the sidewalk in the other direction. Do you say hi or do you like look away?
I say hi.
I say hi, but it's really
They're
awkward.
like they're all old people. So like
It's all the
they're
old
like hi. It sounds really nice.
Really nice.
So I say hi.
I say
I
hi, and
always say
another
hi.
person's like hi.
Well,
but we
you
just
didn't
awk-
say. We didn't listen to this.
also because we don't see the distance, right? So then we say hi, then we're like awkwardly just walking up past a couple more steps to like pass each other.
Yes.
It's a complicated.
Okay, I love them. I love like. Okay. I get that. I get that.
Okay, it's a number. That,
No, wait. Is it not
It is.
Why are we using calculators? No calculators.
but it's
If I do not tell you to use a calculator, don't even get your calculator out. You can do fractions, AP Calculus students. Come on. It's not as much work as you think. No.
Yeah.
No
The
decimals.
word is decimal.
I am going to convert you to a fraction person by the end of the year.
But
Hear my words, I promise you.
everyone
Wait,
else makes it
your name is Ryan. Ryan, by the end of this year, you are going to say, you know what, I actually do like fractions better.
Resist, right?
Very good. And you're tired.
Yeah. Wait,
Good job.
I already forgot. Shoot! I hit. I was recording the whole time. I was thinking I wasn't,
Oh,
but it's because I froze the board.
Oh, I guess I heard her whole discussion of the stools.
They
Yeah.
heard the whole discussion of the stools. That's okay. All right. Well, let's go ahead and get into it then, since the people who are watching this will be waiting for 5 minutes. So, all right, Pranav, how are you? Good. What's the first thing that you need to write for this? F of x is continuous. Now, if I just write f of x is continuous, is that a true statement? On the interval, right? Because if I just wrote it's continuous, would that be true? No. Where is it discontinuous? At 1. How do you know? Because you're divided by 0. Well done. Good job. Okay. So f of x is continuous on our interval. Check. Good. So, Charles. Hi, Charles. How are you doing? You're tired too? Everyone's tired today. All right. So, Charles, can you tell me the next thing I need to figure out? What should I find? What's the next thing I need to find? Group, help him out. Yes. Yeah. That's very So, yes, f of 5 over 2 and f of 4. Here we go, fun with fractions, right? So, 5 halves squared, that's 25 fourths, plus 5 halves over 5 halves minus 1. What did I teach you 2 days ago? Whenever you have a complex fraction, you multiply the whole top and the whole bottom by the LCD. What's the LCD? 4. Multiply the whole top and the whole bottom by 4, and what do you get? You get 25 plus 4 over 2 cancels to 2, so plus 10 over 5 halves times 4. So the 4 and the 2 cancel to 2, so you get 10 minus 4. 35 sixths. Right? Okay. All right. I really want you to learn this method. Right? Multiply whole top, whole bottom by LCD. Just fractions gone. Right? Okay. By the way, well, we'll talk about this in a second. So f of 4. So we get 16 plus 4 over 4 minus 1, so 20 thirds, which Anthony said was 46, which is the hardest word in the whole world to say, 6. So to get the X, the TH, and the S all in there, it's like crazy. Okay, so the question is, I never even asked. Hey, Zuhair, what's our N? It's 6, right? This is our N. Is 6. How many sixths is 6?
36.
Good. Yes, Zuhair. Well done. Okay. So that's okay. 36 sixths, right? Is 36 sixths in between 35 and 46? Yes. So because of that, we can write f of 5 halves less than 6 less than f of 4. Whenever I'm writing my little compound inequality, check, I always use function names. I feel like if I write the numbers, it's just silly. Like, it's like saying, hey, 1 is less than 2, which is less than 3. That's amazing. It's true. I feel like using the function names is more embedded with the theorem. However, if you did on your paper write f of 5 halves equals this, and then you wrote this number, it'd be fine because you already have equated them. So I would accept it. Yes, Susan? No, I don't care. I did it so that you could see that 6 was in between them easily, but yeah, that's up to you. Yeah. All right. Good questions. So now, Alec. Hi, how are you? What is the last thing we need to write? The conclusion statement, right? And every conclusion always starts with the same words. Therefore, by the IVT. And even on the AP exam, you can abbreviate to IVT. They know what IVT means. So, all right. Therefore, by the IVT, now we're going to rewrite our original problem. There must be at least one value C in the interval 5 halves to 4 such that f of C equals 6. You can write that all out in words, and it'd be perfect. I'm going to use a little shorthand. All right? So, I wish I didn't write so big. I guess I can move this whole thing down a little bit. There, so I can see it and write it at the same time. Okay, therefore, by the IVT, there exists one value C in 5 halves to 4 such that is also like a backward E, but it's like a curvy one. So such that f of C equals 6. So this symbol right here means such that. If you ever wanted to know math shorthand. When you are in a higher level, how many of you are going to take higher level math? Good. When you're sitting in your higher level math class and 99% of what you do is theorems and proofs, you're going to appreciate knowing some shorthand. Because you write there exists, therefore, such that like 10 million times a day. So, okay. Let's do, I think we have, oh, it's Bad Joke Wednesday. All right, I'm going to pause for 1 second. All right, Bad Joke Wednesday is done. We're going to do 2 multiple choice problems, zip through 1 more question, and then we are done with our notes, and we're going to go back to our quizzes. So, this first one, this is from 1998. It's problem number 26. It was a multiple choice question. You have the cute little table above. It says, if f is continuous from 0 to 2, and has the values given in the table, the equation f of x equals 1/2 must have at least 2 solutions on the interval from 0 to 2 if k equals which of those numbers? Now, it doesn't look like an IVT question, but this is an IVT question. But if you don't even know the IVT, you can still get this. My suggestion to you is to sketch a quick little picture and think about it, discuss, all right? Take a minute, discuss in your groups, see if you can figure it out. Go.
So is it the end? No, I mean like.
Oh,
that's
N.
What N? Actually, that's the number, that's the Y value. So you're trying to find
Oh, it's A.
really what?
Brian's got it.
Because like, the y values are between 1 and 2, right?
Oh.
And 1/2 is below both. So if you want to go 1/2 both, you have to go under it and go back up. And the only numbers under 1/2 is 0.
Wow, you got it. You got it.
Okay, so you have your y values of 1 and 2, right? And 1/2 is below both of those, which means the graph has to dip down before it goes back up, right? And if you want to go through 1/2 twice, that means to go below 1/2.
Okay, yeah, that
And
makes
the only one below 1/2 is
Quiet.
0.
You already come up with an answer.
So that's how you know it's Y.
Yeah.
I guess what that is. So, I guess fractals, if you just say like 0 Y values, because, well, then I think I get it.
All right, let's talk about this. So, Nidhi. Hi, Nidhi. How are you? I'm doing great. What did your group get for an answer?
A.
You got A, which is 0, which is correct. Can you, or your group, but I would prefer you, can you tell me why it has to be A?
In order for it has to dip essentially in order to hit half 2 times.
I love it. That's a perfect description, right? So, if f of 0 is 1 and f of 2 is 2, and you want to hit a half somewhere in here twice, right? So there's our 1, there's our 2. If you want to hit a y value, right? This is a y value of a half. If you want to hit a y value of a half twice, if you're at 1, if you're at 3, that doesn't force it at all, right? So you could just be above it the whole time. Same thing with 2, same thing with 1. If your y value at 1 is a half, you have to hit it, but you only have to hit it once, right? You could just dip, touch it, and go back up. So the only one that forces you to hit 1/2 twice is if you go down to 0, right? And then go back up. Of those 5 values, that's the only one. Does that make sense? That is an IVT question. It just doesn't, it's disguised. So it's an IVT question in disguise. All right. One more IVT question. This one's from 1997. We're going back further. So, someone just went, wow, that's really old. So 1997, just in case you're curious, I took the AP Calculus exam in 1988. So 1997, BC number 81, let f be a continuous function from -3 to 6. If f of -3 is -1 and f of 6 is 3, then the IVT guarantees one of these 5 things. This one's a little bit harder. You really have to know your notation well to be able to do this. So discuss, think about it for a little bit, see if you can figure it out. I give you maybe 2 minutes. So this group right here, Mahika's group. Are there any answers that you could just eliminate? A.
Yeah.
You can eliminate A. Why? Whoa. Whew. I did not want to do that. Let's try this again.
It's not always guaranteed, that's why we eliminate.
There we go. Just because this point is here and this point is here, does that mean f of 0 has to be 0? No, then it's gone, right? It didn't say it couldn't be, it just said it doesn't have to be, right? Guarantees means this has to be true. Okay, so that one's out. So, Keegan,
Yes.
what about B? Do you even know what B is?
Isn't it like the truth?
That's really good. I was expecting you to say no because I haven't taught it yet. So that's amazing. So, okay. All right. So B should be out because you shouldn't even recognize it because you haven't learned it yet, right? All right. So goodbye, B. All right. We're down to C, D, and E. Now, C is not an unreasonable guess, but here's what C says. C says that the Y values have to be in between -1 and 3 for all x on this interval. Do your Y values have to get from here to here? Are we only allowed to be in between them the whole way? Or can I go outside of them? I go outside of them, right?
It's guaranteed.
Right? I don't have to stay in between the whole way. Right? I could,
Oh.
but I don't have to, right? This guy is out. We're down to D and E. F of C equals 1 or F of C equals 0. Both are in between the Y values of the endpoints. So it's down to just knowing if C is an X value or a Y value. So, Jennifer.
Yeah.
Oh, sorry, other Jennifer. Okay. Jennifer, is C an X value or a Y value?
Oh, why?
You're so close. It's an X value. Okay. So C is an X value because look, it's they didn't write it here, but they're saying like F of C equals 3. Like C is your input, right? K or N, those are your outputs. So, all right, that was good. So C is an X value. So does our C need to be between -3 and 6 or -1 and 3? -3 and 6. This answer is D. The function has to hit a Y value of 1 for at least one X value between -3 and 6. All right. I know. You're thinking, whoa. If that is like kind of, if your brain's like, I didn't get this and I don't know if I could get this on a test, you just started, right? You just learned this, right? This is day 1. So it's okay to still be grappling with it, right? I expect you to grapple for a while. So grappling's okay, right? We'll get it down. You'll be just think, in 5 months you'll look back and be like, oh my God, that was so easy. So like, but now you're in grappling mode, right? Okay, I don't want to do the AP problem. Instead, I'm going to have you guys pull out. Watching the recording, I'm just going to reveal this so you can see what's going on. So explain why there has to be a value. It's because H is continuous. You have to find H of 1, which is F of G of 1 minus 6. So you have to plug in, find G of 1. G of 1 is 2. F of 2 is 9. So F of G of 1 minus 6 is 9 minus 6, which is 3. You do the same thing for H of 3. And then you say, hey, look, -5 is in between -7 and 3. Therefore, by the IVT, there must exist some value R between 1 and 3 such that H of R equals -5. And here endeth the lesson.